Hello and welcome to IEEE of Robotics podcast. Hello, Professor Suo. Thanks so much for joining us in the podcast. Such an honor to have you. So I would like to ask you first how you would like to, first of all, introduce yourself for the people first time, maybe listening to podcast, and also how you would like to define yourself.
Thank you very much for this invitation. So I'm a Zhigang Suo,
Yeah.
a professor at Harvard University, engineering professor. My field is solid mechanics.
Mm-hmm.
We study materials, how they deform, how they fracture, uh, and also try to develop new materials to have
Mm-hmm.
suitable properties.
Okay, wonderful. Yeah. And how you would like to define yourself? Do you have any other definition for you beyond being science? Any definition for yourself?
Oh, just engineering professor. I guess, yeah, yeah. My
Okay.
field is solid mechanics.
Yeah.
Yeah, yeah.
Yeah. Great. So I'm curious to ask you about your childhood. Do you have any memories as a kid about interesting science technology? I'm really curious about that. How was your childhood?
Oh, childhood. So I was born in China.
Mm.
Yeah, China is an interesting period, but somehow I was very lucky to dodge all the troubles that many other people, Chinese, have experienced. So I was
Yeah.
born in 1963. That
Mm-hmm.
was after famine,
Yeah.
before Cultural Revolution. There was a golden period in Chinese history,
Yeah.
a few years. So I was born during that. And then, of course, I went through Cultural Revolution, but it didn't
Yeah.
harm me. It harmed a
Mm.
lot of people. So during that Cultural Revolution, I was mostly in kindergarten, in,
Yeah.
in elementary school. So
Yeah.
these are places were even protected
Mm-hmm.
during Cultural Revolution. They did not harm children. So it was extraordinarily lucky. And then I don't know how much you know about this Chinese history. It's interesting, very intriguing, so unusual. Because I stay in America for more than 30 years now. So when I was in China, I didn't know anything special, but now
Yeah.
in hindsight, it was such a special period.
Yeah.
Um, so, but so during Cultural Revolution, that was between 66 to 76.
Mm.
Uh, for much of that time, university was closed. My parents were both university teachers. They taught um, Russian before Cultural Revolution
Oh.
and English after. That's another interesting thing. But during Cultural Revolution, university was just dysfunctional. It's not a normal place. But we lived on campus. I
Mm.
was not in the university. The university was reopened by this great man, Deng Xiaoping. He's
Mm-hmm.
just extraordinary man.
Yeah.
For some period, he was a leader of China, very practical, very wise person. He reopened the university in 77. I entered university 81. So I was not harmed in
Mm-hmm.
any least bit of way. No, just a normal university for me. At just exactly the right age, 18 years old, I entered university and graduated. Upon graduation, it's just extraordinary. I signed up to be a graduate student
Mm.
with a professor by the name Shin Ji. Last name is J.I. He somehow felt I was good enough to be sent to Harvard. Harvard, not any other place, just Harvard. He had a fixed notion, I need
Yeah.
to go to Harvard, because he previously already sent a very good student to Harvard, who was very successful. Wajin Gao, I don't know if you recognize this name, just outstanding mechanician now.
Yeah.
Yeah, he was doing very well and also sent by Professor G to Harvard. So Professor G had a notion. Harvard had, at that point, 4 solid mechanics professors. So Professor G's plan was to send 4 of his students to Harvard, one for each professor. He actually realized that more or less eventually. So I was the second to be sent. So at that time, in 85,
Mm-hmm.
yeah, 85, just by pure luck, Professor Hutchinson went to China for giving some talks. So during these years, not many people go to China, went to China. So for big shot professor, Harvard professor going to China,
Mm-hmm.
the Chinese scholarly community would arrange a tour within
Mm-hmm.
China. So my hometown was Xi'an. Xi'an was the ancient capital. If you arrange any tour in China, Xi'an is a must stop. You just cannot avoid it. So,
Yeah.
yeah. And Professor G visited my home university, and my own professor, Professor G, decided I should go to Harvard, right? That was his plan. So he introduced me to Professor Hutchinson. At that point, all Professor G needed to say was, oh, I have a new student. And this student is comparable to this other student you liked.
Yeah.
I was almost accepted on spot. At that time, I barely speak English. I actually didn't know much about Harvard at all at this point.
Wow.
I was an engineering student, right? Harvard wasn't on the radar screen, and not actually. And so not a single university in the United States were really on my radar screen. Xi'an is a little backward place these days. It's an ancient capital, but
Yeah.
falling off the radar chart for many, many centuries, for
Wow.
practically 1,000 years. The last time Xi'an was doing well was in
Yeah.
Tang Dynasty, 1,000 years
Mm-hmm.
ago. So we're talking, speaking about China, the measurement is not a day, year, it was about 1,000 years.
Yeah. Yeah. I would like to stop here because I think it is really wonderful that your supervisor just believed in you and give you opportunity. Maybe it wasn't in your rather, but how do you see now, because you're now a professor, how you see this kind of this relationship? I think that's believing so much in you and sees the potential to be a renewal professor in the future. When you look back about that, this is maybe a life changing for you to have such a professor like that
Yeah,
in your
Professor G seemed to be quite unusual in hindsight.
mm,
Himself he's still alive, 90 some year old,
yeah.
still in good health. He seemed to have unusual vision of people and topic.
What do you
Yeah,
mean unusual? What do you mean by
yeah,
unusual?
unusual. For example, in these years, in China, um, he kept up with outside research, international research. Himself also visited United States as a visiting scholar for a year or two in Delaware. Yeah,
Yeah.
he in Delaware that was used to be a center, still is a center for composite research. So
Mm-hmm.
he had some background. So Professor G himself is an outstanding scholar. And furthermore, at that time, he was already a department head, so
Mm-hmm.
also politically skillful. Yeah. Uh, so he also had quite few very successful students. That cannot be accident.
Mm.
So if one person has multiple very successful students, that cannot be accident.
Yeah.
Yeah, you ask how, I actually don't know. Good question. Never really thought carefully. It's just, I guess, maybe he's inherently good-hearted, smart person. He didn't really keep his best students, just his students. There's many people doing that for good reasons as well, right?
Yeah.
But he wanted to find for each of his best students, good students, to a bigger opportunity. So this is in mid 80s.
Mm.
So there was no question in
Yeah.
hindsight, the biggest opportunities was outside China.
Wonderful. This is a really wonderful
Yeah, in
story.
80s. That's extraordinary. You're
Yeah.
right. Yeah,
Yeah. So I'm curious about your journey from China to Harvard
yeah,
back in time. Was it challenging for you to settle and just blend? And also how the passion to material just developed, maybe, I don't, maybe doubled, I don't know. How's this journey to be in different culture and still barely speak English at this time? So how it was for you to be now established and one of the renewal professor in the field, yeah, back
yeah.
then?
So yeah. Thank you for asking this. So I came to Harvard as a graduate student um, in '86.
Mm.
So by that time, I could already write English quite well. My parents were English professors.
Mm.
So also I spent my college years really study English very hard. So I could write very well, very logically, I guess. The grammar still have problems, but I liked writing even then. Uh, but I could not speak. So listening to English was even harder. Because speak, you speak slowly if you don't speak well.
Mm.
Listening, you have no control of speed. Listening was the hardest. So, for in the first semester, we were required to take 4 courses, graduate courses. At Harvard, courses are serious. It was a very difficult period of time,
Mm.
first semester. Courses are hard. Most time I couldn't understand in class. And also one particular topic was taught by Professor Spapen. Now he's a dear colleague, Professor Spapen. He was teaching material science. Was a totally new topic for me. Not very mathematical. I was very mathematical then, but a lot of physical intuition and also a lot of connection with the
Mm.
physical facts. So it was a graduate course. He, of course, assumed multiple undergraduate courses. You should already, uh, have taken these undergraduate courses, so you know part of reality. I did not.
Mhm.
So that was very hard. Plus, I couldn't understand his version of English. He was actually Belgian. So I read a lot. Also, in first year, you're just so insecure about yourself. Come to
Yeah.
Harvard, right? Great people, and people also don't talk about their grades. So I constantly assume I must be at the bottom of the class, right? So I was struggling. So eventually I got OA in 4 courses. So after first semester, I begin to have some confidence, but that's only in courses.
Yeah.
First semester, Professor Hutchinson was not on campus. He was on sabbatical in
Mm.
Denmark. I had no research. So today's students will be upset if you don't do research. But back then, we were supposed to take 8 courses for the first year. It's not uncommon for not doing any research for first year. So my own research started in the summer. of 80, this will be 87. Professor Hutchinson was back from Denmark after sabbatical. He gave me a topic. I still remember that topic. And then he disappeared for his summer research place that was in California. It's a big job for him. He was on some defense council or something. He always went, but at that time I didn't understand. So, but I didn't know what to expect, right? So he disappeared. I was doing this problem. I actually finished that problem before he came back. I got a solution. It's a mathematical problem. It's something about finding singular stress field at a corner, three-dimensional corner, not crack tip, at a corner. So in hindsight, it wasn't that difficult problem. But I was proud of myself. I figured out. Of course, I didn't know why Professor Hutchinson asked me to solve that problem. I had no real connection with the reality. I have a connection with mathematics.
Yeah.
So, and he came back. He was totally disinterested in my solution.
That's
He was not. Yeah. He did not even bother to listen through my explanation, what I have found. But he said, "Oh, Zhigang, I have a new set of problems for you."
So what happened?
Yeah, the new problem was, it turns out to be important. I didn't know at that time. It is a problem about laminates, thin film coatings on substrate. And he could explain to me over the days that why that class of problems is important. It's important for composites, for computer electronic packaging, right? Thin film on plastic, metal on ceramics, that kind of thing. Of course, the detailed background came gradually. But in the very beginning, it was very clear to him and also to me. He made it clear to me. It was important. And at that time, he was collaborating with Professor Evans in California, Santa Barbara, material scientist. So he directly connected me to a source of physical situation. That was what I needed. Because applied math, at that time I was just a mathematician, right? Applied mathematician, know how to solve equations. I didn't quite know how equation solutions are related to physical reality, or even further away from how that physical reality to engineering, to something people. So both connections were made to me after months getting involved in the project. I didn't even know that's important. I was a graduate student, right? Just an undergraduate student, applied mathematician, solve differential equations. That was my thing. I was actually quite good at it in hindsight. So I rapidly solved a lot of problems. I didn't know application, but then people Evans and Hutchinson made it clear to me how each solution could be used in relation with the experiments and in relation of the development of composites. So then by the second year, this will be 88, I could propose new situations, could lead to new application, new experiments. So in hindsight, maybe I was unusual because now I see many graduate students, not many graduate students can rapidly make this transition from a student with a certain background and learn something quickly and then propose new things. Still related, not new field, still same field, but all kind of variations. So by the end of, I think I was quite funny. So I guess by the summer of 88, Uh, yeah, let's say, yeah, or yeah, there's something like was spring 88, quite early on. Hutchinson
Mm,
already asked me, oh, Zhigang, we should plan for you to graduate. Professor Hutchinson, I only came here 86. I
yeah,
cannot possibly graduate. I don't even know how to begin research yet. Hutchinson said, oh, you're that new? I didn't realize. So ultimately, I actually graduated in 89 in,
mm,
so defended in April 89.
yeah,
It's actually less than 3 years. It was, in hindsight, it was extraordinary.
yeah,
Uh,
yeah,
yeah, uh, but it had a huge drawback later.
yeah.
So yeah,
I think this is a really good story since you related to how graduate student can make this transition, and then
yeah,
you bring a problem and solution as well. And
yeah,
from your story, you have absent professor at the beginning. He's brilliant, but was absent, and you take that charge to solve the mathematical problems, and doesn't make sense to you
yeah,
unless you physics. So
yeah.
maybe I can just ask you: do you think if you were not connected to physics, you were able to do what you're doing in these 3 years? Is this missing piece for you?
Missing piece, yeah. In the beginning, my first problem Hutchinson gave to me, yeah, I just solved it as a mathematical problem. I kind of mechanics is at least in terms of image is quite related to physical reality. It was no, not too abstract, but
Yeah.
still you need to uh, show how real people do experiments. So what does that solution, uh, how does that solution impact what other people do, right? I always wanted to know that. But for the first problem, I couldn't see that. I still cannot see that. Yeah. But from second problem on, um, yeah, was very clear to me. I can even develop a variation how to connect to other people or other experiments. That was tremendously satisfying. Also, Professor Hutchinson wasn't always absent. He was absent for the first year, and in subsequent years, he was on campus.
Mm,
We spent time together. Yeah, rapidly finished multiple papers. That was very helpful. In those years, even though publication themselves are slow, takes about 1 year or two to write a paper and review. However, we had preprints, right?
mm,
In those years, preprints were sent out to the relevant people, and relevant people already designed experiments and give us feedback how things are used. So I was a pretty practical, guided by practical people uh, through these interactions.
yeah.
Yeah, I saw faxes back forward between Hutchinson and Tony Evans
Mhm.
about solutions I was working on, what's needed, what's missing. Oh, that was very, very helpful.
Yeah.
Of course, nowadays we arrange Zoom meetings
Yeah.
between collaborators, right?
But do you, just a quick question here, when you compare to 80 60 and when you graduated, do you think there's huge difference nowadays, the same vibes and culture or different? Because you speak about very supportive professor who believed in you and also you were a very brilliant student. So
Yeah.
how do you see this nowadays? Is still we have this culture from you, still we have to make effort to bring what we have in 80s, for example, or before?
Yeah. Many things are same, but some things are different. So
Hmm.
same as so among our colleagues, we still see some extraordinary mentors. People had long vision, also can relate, connect that vision to new students. That's all it takes, right? It's not about the professor student relation. It's not about, oh, let me help you rent a house. We're beyond that. We just really need to connect, uh, help somebody start a career with a good set of problems. so that you teach people some kind of vision that could continue, right? We see many colleagues doing that. That's, I think, is the same. What's different is the size of the group. Typical size of group now, at least at Harvard, is larger than before. So when I was a student for Hutchinson, right, his group is typically is a 3 graduate students, maybe 1 or 2 postdocs, 1 or 2 visitors. That's it. So for me, constantly we're going between, it's around 15 people, and my group is a small, modest at Harvard. Many
Yeah.
of my colleagues have more. So that changed the relationship between professor and
Yeah.
individual student. But some of my colleagues manage a large group very well. We have great people like George Whiteside, Joanna Eisenberg, just a name, just go on and on. David Weiss. David Weiss has constantly 100 people. So he has his way of managing through
Yeah.
hierarchy. So
Yeah.
student already learn to perform in a team. So that's different, not necessarily bad. It's different,
Yeah.
very different. Your relationship with your professor.
I think this is really wonderful relationship for being between mentor and mentee. And I'm curious for you after graduation, you're passionate about material. What's something you find maybe you understood about material while you're designing the understanding how the fatigue is happening and correctly sheet? What's something was seeing very interesting for you back then when you were very young that I'm so obsessed to understand the material and how the failure at certain time. What's this kind of question you had in your mind to solve the problem and how you get, because sometimes it is hard to spot a problem and also find a solution as well. So how this tactics for you to figure out this is a problem here?
Yeah.
Is this something, how does this come to you that this, of course, you are passionate and intelligent at the same time, but to figure out the problem and solution, how we
Yeah.
can do that?
You mean identify new problem in a new area? Yeah. Actually, it's a good question. So it seems to be always in me. When I was even in high school, back in high school, my only passion was mathematics. I won many low-level competitions,
Yeah.
provincial, never made to the national. But even in China, make to province was already quite big deal. So I made a quite the top of a province. So even back then, so I like to solve mathematical problem. And what even more is I like to pose new mathematical problems. So I will design new problems. So in hindsight, these are just child's play. But it still requires different kind of skill than solving other people's problem. So we want to pose a problem that's kind of original.
Yeah.
So I have a collection of problems I posted it by myself. In hindsight, it's just a child's play. But that's always in me. I want to do new problems, create new problems. So then, in at university, I had a concentration. My major was engineering mechanics. It is about the design of elasticity, plasticity, fractures, this kind of thing. So in China, undergraduate mechanics training was quite comprehensive. In terms of topics, we already covered what will be covered in PhD courses this country, not to the certain same depth, but certainly same breadth. So for example, we had a separate course on plasticity. In the United States, you'll be lucky you got a course even at a graduate level. The undergraduate already have a course, another course in fraction. undergraduate. It's extraordinary. So back then, when I was a college student, I already, so for each course, these major courses, I already start to essentially write my own textbooks, even then. So I take the notes and then I will reassemble notes according to my own understanding, my own reading. I was always like, just interested.
Mhm.
I end up doing very badly compared to the effort I put in, badly in examinations because I think too deeper, too much, and too many tangents,
Mhm.
rather than fix the task of immediacy. For students, immediate task is pass exams. It has to be, right? So it means you master elementary things very quickly and
Yeah.
very fluently. I wasn't doing that very well. For
Yeah.
each examination problem, I always remember, I always think about it from first principle. Other students already start at the middle. Here's the equation I can use, just use it. I would
Yeah.
develop an equation. So by the end of the exam, I was still at the middle of developing that equation. I was doing fine, but I wasn't as a top of my, it was a top
Yeah.
five, but it's not top student.
Yeah, but this is, may I ask you a question? Because I think this is really a very important point that when you go with your mind and imagination about different aspects of what you're studying, and that was maybe a drawback for you in studying, that later
Yeah,
on it was beneficial for you. Do you think it's just how the education look like that don't encourage you to think in a deeper way? That's
yeah,
something you think is we have to work on that, just think beyond what you study.
yeah. It worked for me, um, at least for the undergraduate period. But now my sons already both graduate from college. They had
Yeah.
their own. They already have started their own careers now. So in America, undergraduate education seemed to serve very different purpose.
Mhm.
The purpose was more about uh, leaving your parents, living with other people,
Mhm.
be influenced by your peers. These, at least at Harvard, that's my impression.
Yeah.
These aspects, social aspects, seem to be much more important than technical learning for average student. That's my impression. Uh, I guess for a very simple, it's not good or bad. It's just difference. For example, one difference is when I was a student in China, undergraduate student. So after graduation, each student was assigned a job. So you're a mechanics student, you're going to study mechanics, right? Either in a factory or in a research institute. You do not find a job yourself. You cannot find a job yourself. Government
Mhm.
plan your career, give you a job, assign you a job, right? So then it means that if you study mechanics, you're working on mechanics. That, yeah, in my generation, even though we were assigned job, um, but most people, my classmates, if they stayed in China, they moved on to do other things, right? They changed. But but when we were students, that was the plan. We planned to work on mechanics for our life. Here, an American student, you're a mechanical engineer. What are you going to do? Oh, I'm going to Wall Street, right? Or I'm going to do computer science,
Yeah.
or I'm going to develop, driverless cars. The opportunities are very different.
Mhm.
No government assign your job, and your job is defined by yourself. So then your technical depth is almost irrelevant to your
Mhm.
success in the United States. That's how I feel. Is irrelevant.
Mhm.
So some of my colleagues are upset, but because I have this Chinese experience, I see the difference. I cannot decide for myself which one actually is better for an
Mm.
individual.
Yeah, and I think that's really excellent point. Do you think maybe because now we have maybe now sometimes it is rare to find a job that
Yeah,
satisfy you And even if you're a professor, sometimes some people could leave it for industry. It's different, of course, of personal experiences. But do you think if we compare about Chinese experience vs US, which one do you think it could be really helpful in growing? Maybe it's just different, but I don't know. You have
Yeah.
both expertise. Which one could be really help in growing? Or maybe challenging. I don't know. How do you see this experiences if you compare which one? Or it depends on personalities. I don't know. Yes.
Depend on personality and also depend on the country, right? So for United States, for all these decades, we already know that, right? From graduate school, large number of graduate students came from other countries,
Yeah.
right? United States can do that, right?
Yeah.
If you're Chinese, you cannot do that. You cannot hope that a lot of people from other country will come to China. So then United States can afford to have a very liberal, non-technical education at
Yeah.
undergraduate level, even though our courses are very technical, but the kind of mastery is laughable. If you just look at a technical, right? There are, of course, brilliant students, but just such a small fraction. So it's a laughable, but it
Mm.
works for the United States. It
Yeah.
works. Yeah.
Yeah. Yes.
So don't want to change because this liberal education does train people perhaps with more creativity, more flexibility, and a more leadership kind of thing, people skill. So yeah,
Yes.
it's different. It works for
Yeah.
United States. Yeah,
Yeah. Yeah. You can
yeah,
imagine. Maybe I'm curious again the relation between the loving for mathematics and the material of passion.
yeah,
And speaking, I think here about the modeling. Because I think when we speak about understanding the material, how they behave, and coming up with physics-based modeling, and just understand how does material behave. How do you see the modeling for you when you just look at material? What's the first thing you consider to model, understand, to see, figure out this is a significant parameter in this material? What's a significant behavior? How does this relationship go hand in hand with mathematics and material understanding? Since we lack this sometimes, we go on the lab, do empirical work, and sometimes optimize trial and error. But when you look in mathematics, it is just hard to come up
yeah,
with a model.
yeah,
How this work for you? Yeah.
yeah. So a very good point. So my field is solid mechanics. Solid mechanics has a range all the way for classical end is you use existing materials to design bridge, design building, design airplane. So in my early years, the goal were design composite for high temperature application. At that point, it was a combustors, ceramic matrix composite for combustors in airplane. Even though myself are not designing combustors, but it was very clear, made very clear to us by the industry that that's needed.
Yeah.
High temperature materials for combustor, for chemical, just a better combustion, more environmentally friendly combustion, and also for fuel economy. It was made very clear to us. And why you need to have a high temperature material,
Yeah.
that's why. And a high
Yeah.
temperature, which are the high temperature material? Has to be ceramics. It cannot be other kind of materials. And how do you make use ceramics? Ceramics is so brittle. How can you make a brittle material survive engine environment, airplane, and your customers are willing to take your airplane? So it was very clear the connection between our research to the goal. So I was embedded in that culture, even though I myself was not designer of aircraft, not even developing materials myself at that point, but the connection was very clear, very helpful. So that's one kind of application. The other application made a huge impact on me was electronics, microelectronics. That was also new at that point. So I don't know if you probably realize that, right? So we have good success in designing bridges, not because we had finite element code or we understood elasticity better. That was only for recent decades, right? For thousands of years, people design bridges by failure, collapse, and you improve. And people have some understanding without calculation. Some understand, then design bridges. Some bridges survive, other bridges do not. Some people actually learned. So, but when you design chips, you do not have that luxury. You don't have 100,000 years of experience for chips, right? Every year and a half, 18 months, you need to design your next generation of chips, different scales, maybe different materials. So that put some understanding and quick experiments to such a premium value. So mechanics really come in. So I work with people at companies, mostly Intel, really give me eye-opening how mechanics was used in developing new structures. Very helpful. So, and during that interaction, it became very clear what kind of things can be useful.
Yeah,
Yeah,
that's
very
wonderful.
good. So I get many inspirations through practical needs. Of course, I also have a little skill, just turn that practical needs, not only solve their immediate problem, and also twist that into an academic problem, kind of more fundamental, so that can broadly appreciated by colleagues.
Yeah, yeah.
Yeah,
I
yeah,
think that's really, I think, important to have impact and also
yeah,
maintain the academic research. But I'm curious about the structures you mentioned. Very important example in chips. You don't have this luxury to
yeah,
test for many years.
yeah.
So how do you see the relationship between the structure, maybe how to optimize the structure and design this new material? How you figure out I need this new material, and that's what is missing. Can you give an example for that? How the relationship between morphology, structure, and new material?
Yeah, excellent question. So one specific problem faced by Intel and the entire industry in
Yeah.
almost starting from beginning, but in 1990s, a class problem was made very clear to me. So it was about adhesion between different materials. So when you make a chip, you need to adhere maybe a ceramic to a semiconductor and a metal to that ceramic, right? Many, many layers. Right? You need to have an integrated structure, right? So then the adhesion become important, right? Otherwise, you can have debonding. So adhesion, so today many people say, oh, I do ab initio calculations. After so many decades, that approach is still a failure. It's hard to do interfacial adhesion. Because adhesion is not a property of a given material. It's a property of at least two materials and also how you process it. So during the adhesion process, maybe you have oxygen, maybe you have a nitrogen, a different pressure, just so many variables, temperature. So it's a process variable, right? So now the problem was the following. So when Intel in those days, they said, oh, I have a new chip. I need to develop a new chip. In this new chip, I introduce a new material A into the structure because it has extraordinary low K dielectric at that point. Low dielectric constant has nothing to do with mechanics, but it's a new material. Need to adhere well. We had no experience integrate that material into the chip. That's the problem, right? So they're, how do I learn about this? They already knew computation is hopeless. Just never get any useful result to this day. So my computational colleague will be upset, but I need them to show evidence that was useful for this problem. It's not. All right, so then what Intel did was test it out. Oh, okay, I have this new material. Let me put this material on this other material, turn the oxygen knob. Here's how I process so many minutes, so many seconds at this pressure, and then see how it fail or not. That became a problem. So when you just deposit film, think about this film could be, 100 nanometer. The film is so thin, it doesn't have much load. So nearly everything you put on top of it doesn't really fail. So how do you know it fail or not? You need to build whole devices. Now you have a layer upon layer upon layer. These other layers will apply load. So how do you know how much load? Because when you turn on computer, there's a temperature change. So in order to simulate that temperature change give you thermal stress. So the industry will do thermal cycle test. So thermal cycle test for 3 months. And you have the report, your interface works or not. So then the industry colleague said, I only have 18 months. I need to turn out a product. And each knob I turn, you need to report to me after 3 months.
Yeah.
Whether that knob is correct or not. If a knob is correct, great, 3 months. Knob is wrong, do I do this again? Another 3 months? You see the problem? Your feedback time is too slow for you, specific for this problem.
Yeah.
Just because you need to build a whole structure and the way you apply load is doing thermal cycling. So then how do you do this? How do you do this? So the solution, it turns out I only played a minor role in ultimate solution. I was involved in the beginning, but the crucial role was played by this colleague at Stanford, Rainer Dowsker. He was my hero. With my friend at Intel, Chin Ma, the pair, so Stanford, Intel, they're so close together, right? Chin Ma was a very good friend of mine. I was so far away. I was at UC Santa Barbara, so I did not involve in the final solution. The final solution turns out to be very simple. They say, okay, so when you make your film, right? So that then they glue another chip on top, just glue it instantly and directly do peel test or bending test, see whether interface debound or not. So because they have a previous experience, what kind of load causes fracture? If this load causes fracture, that won't pass 3 months test. If you can pass this test, you will pass that test most likely. So then they turn this thing very rapidly. The moment you turn the knob, this morning you turn the knob, the afternoon I do a rapid test for you. And you already know it works or not. So now I simplify a little bit. So in order to relate the fast test, what we call accelerated test, to the real test, you need to understand mechanics well enough. So made some contribution to these guys' final solution. So that shows me how mechanics actually is used, really literally save huge amount of money for Intel, and also made colleagues at Intel understand, see how academic research could actually help. So for many years, I had a steady stream of support from Intel, not only in terms of money, they provide some money, and also steady stream of just good problems they feel important and they couldn't solve immediately. They just have we had a monthly meeting. You asked me how to identify problem. I use other people to identify problem for us.
I would like thank you for this example, I think very concrete and also clear for student and myself
Yeah.
how you can spot problems. And I'm curious for the second part because you're so fascinated, I think, or maybe obsessed by friction mechanics. Even on Twitter, you really make an excellent thread about 100 years of toughness. And thank you. Yeah. But I'm curious to ask you how you can, because you also do that, how you can design material that maybe delay the fatigue or the crack.
Yeah.
Since you play with the morphology, and honestly, there's no lot of research how you can compute or maybe combine multi-material in a certain structure so that you can delay the fatigue. Or maybe I'm asking you, do you think we can design material maybe never damaged? If we
Mhm.
speak in Intel example, for example.
Yeah. Yeah. Yeah.
Yeah.
Yeah. It's an excellent question. So the fracture you have mentioned as a tweet, a thread, a long tweet. I don't know how many tweets now. That thread is called 100 Years of Toughness.
Yeah.
I'm still in the middle of converting these tweets into a review. Next year, 2021 would be 100 years anniversary of the Griffiths paper, widely regarded as the paper that started fracture mechanics. So, and I'm trying to, yeah. So now the fracture, of course, the fracture has been with the humanity and with animals since the beginning of the life, very, very important aspect of nature. So people knew about this, but really the modern way of connecting fracture, this macroscopic thing, so important to animals and humans, to all the way to atoms. That connection was first really made by this man Griffith
Mm.
100 years
Yeah.
ago. Before that, people mumble jumble. Uh, so it wasn't total surprise if Griffiths did not make that connection. Other people would, because 100 years ago, important things happened. People essentially for the first time really connect to everything else, to atoms, right? So it wasn't a surprise why 100 years.
Yeah.
Yeah, wasn't a surprise. So anyway, for fracture. Now fracture, yeah, it has many decades of development. Uh, so by the time I got into the field, the Hutchinson and another professor at Harvard, Jim Rice, these two men, when they were young, they made seminal contributions to the development of fracture. So by the time in late 80s, I was a PhD. The consensus was the topic was over. Fracture mechanics was over. It turns out these guys are over optimistic. So for something as important as a fracture, the topic was never really over. Just some stage is completed. There are other things. For example, in late 80s, we face the opportunities or troubles of applying fracture mechanics to microelectronics. The chip story I just told you, and also apply fracture mechanics to develop composites, ceramic composites. So these were not in previous, textbook or people's learning. So and then it's funny when I was teaching at Princeton. So I moved to Princeton in 97, right? Then I left 2003. During the Princeton years, Princeton was also a small campus. Have you been to Princeton campus? No, well, yeah, if you have an opportunity, you should. It's just a fascinating campus, very small, very pretty. Small has its a nice feature. So my office neighbor neighboring office, just a few offices down the hallway, was a professor by the name Sigurd Wagner. He was older than me, now retired. Incredibly enthusiastic. So I was so proud to him because he was an electrical engineer. I was proud. Oh, I work with Intel, help Intel to solve their problems. Sigurd said, Zhigang, Intel is a past industry. They already shipped their processes to Asian countries. If you want to stay in university, do original research, you should not do microelectronics. You should work with me on macroelectronics, MA, macroelectronics. So he introduced this word macroelectronics to me. He said, look, Zhigang, everybody wants to make things small, but people will never be small. Will be our size forever. So at that point, he was working on large area display. He said, people want to have large displays. Nobody wants to have small displays. He didn't foresee children like to have cell phones. In these years, this is in the 90s, right? People want to have a giant screens. Giant screen has separate problems from microelectronics. This is a cost become very sensitive, right? You need to process a large area electronics. So another set of mechanics problem, right? That thing quickly morphed to stretchable electronics, now we know. So Sigurd was a father of, many people regard him as a father of stretchable electronics. So I would think I probably was a nephew of the stretchable electronics. I worked with Sigurd. I got order from Sigurd, whatever he wants to do. So, that introduced me to another set of materials. One thing leads to another, leads me to work on soft materials. So you need to be stretchable, right? So elastomer was already at Princeton. We started to interface with the people who need to work with PDMS. So we wrote several papers with Sigurd, all because of Sigurd, and the Sigurd people want to have answers. So you ask me, how do I identify new area? New area just fall on my laps. I don't really need to identify them; they just fall. So yeah, I became a nephew of stretchable electronics. So and then came to Harvard. Became a cousin of soft robotics because Whitesides wanted to do soft robotics. Yeah, both George Whitesides and Sigurd Wagner not only said, Zhigang, I want get you interested in working on stretchable electronics and soft robots. They also put money on table. Zhigang, here's the money. Hire people to work on this. Okay, sure.
Yeah,
So yeah.
so how it for you, just to starting maybe in soft robotics, since it's highly dependent on material, do you think how far robotists understand materials? If we wanted to design them in a certain shape, or maybe adding new functionality, or now we're speaking about how we can design a material that have its intelligence and compute everything internally. If we speak about smart material, how do you see robotists understand the material? And for example, also we speak about with Professor George Whitesides in the podcast since 1 year ago about how we can maybe extract the beneficial nonlinearities in the material, how we can figure out that, how we can embrace these nonlinearities and not get rid of them. Maybe what could be useful like buckling, etc. How do you see this area if robots understand them, and how you see nonlinearities in the material as well?
Yeah. You mentioned the buckling, the word buckling. Yeah, George Whitesides. So for short period of time, he said, "Oh, Zhigang." I also talked to other people as well. Oh, I learned this instability from Zhigang. But at that point, instability was very important and very interesting phenomena for mechanicians.
Mm,
If you're a mechanician, you have to be interested in buckling. So, and then early on, even before I interacted with George Whitesides, we show how you can use buckling to achieve something extraordinary. So one particular example was working with uh, applied physicist um, uh, Siegfried Bauer, who also sadly passed away a couple of years ago.
mm,
So working with his team and also his very brilliant student. Um, you probably will interview him if you haven't. This guy, uh, Christoph Kaplinger.
oh, I
Yeah,
tried, but he moved to Germany. I think he now
yeah.
direct.
He is now Germany.
Yeah,
So, yeah, Kaplinger
yeah.
was Siegfried student. So Siegfried at that time already collaborated with me. Siegfried sent Kaplinger to my group to,
Mm,
to interact with my group. So then every month, or I forgot, is it every month or every 2 weeks, we had, online. That time it was a Skype. There was no
mm,
Zoom yet, Skype. Uh, so we interact. So we work on one specific problem. It's a dielectric elastomer, you probably heard, apply electric voltage to
yep.
cause deformation. So we achieved, at that point, it was a world record. You just apply voltage. So I can turn area 1 by 1 area to 4 by 4 area just by apply electric field. Just enormous deformation by electric field. The way we achieve that is through an instability. So, and then, so I'm a mechanics person. I didn't do experiment at that time. Bauer did experiment. We did some design, and we could explain mechanics really in simple terms. And George Whiteside just loved it. Wow, this instability can do something you couldn't do in normal, just normal material instability. But in hindsight, for material scientists, we also always know instability is just a phase transition, right? So, so during one Christmas, George and I had to rush through our MRSEC. So we just online back and forward about a proposal. So I was saying, wow, this instability, mechanical instability at the macroscopic scale, really is just what material scientists are familiar with. It's just phase transition. You have sudden rearrangement in materials, sudden rearrangement of atoms, and at a macroscopic scale, you have a sudden rearrangement or discontinuous rearrangement of the shape. It's the
Mm,
same mathematics, same phenomena, just a scale is different. So we could connect these two things and uh, do many things. So George was incredibly enthusiastic about that idea. He just made enormous upgrade. George, his imagination just indescribable. Once he understood a gist of idea, he will
mm,
amplify that idea. So eventually I had to learn mechanics from him, put it this way.
oh,
He would teach me mechanics. Zhigang, this is how mechanics should work. Okay. Yeah. Anyway, but I could, so my little contribution was because of instability was such a long tradition in mechanics. Mechanics,
yeah.
people know a lot. One of my strengths is once I understood something, I could explain that something to other people. So in this case, I only need to explain to one person, that's George Whitesides. And then he explained to the world how we should use instability to do all kinds of things.
Yeah, that's really you're wonderful. Yeah, I think we're still in the field figuring out how we can use this nonlinearities and instabilities to get
Yeah.
interesting information.
Yeah.
And I'm
Yeah.
curious to ask you, yeah, I think because we are closing then I don't have too much time, I think, so I just have a few questions. The first one, what do you think maybe could still maybe interesting for the field of soft robotics and soft material design, and we're not focusing yet on that? What's something you think we have to make effort in this direction? Maybe you think still missing a lot of attention, and we have to maybe figure out that, or maybe make effort and research and considering this problem. What could be that thing from your experience?
Yeah. So from materials aspect, so uh, one aspect, of course, is mechanics itself.
Mm,
If you look at robots and also machines, our experience in the past, uh, very, very few successful examples we have actually
yeah,
using elastomer and hydrogel making anything. So one outstanding example, of course, is the tire. Tire is a highly engineered structure and it uses rubber, right?
mm,
Right. But a tire itself is so far away from a functional robot, right? For the Christ's sake, the tire doesn't deform very much.
yeah,
So it is engineered in particular way over many decades to the extent that very few people can actually explain to you what's actually the science and the mechanics of tire. You can take a lookbook, the papers, there are thousands of them, but none of them are translatable to any other applications. Just too much
mm,
depth and I would say too little scientific understanding that's translatable. So I'm not saying these researchers are not scientists, but just because this is such a commercial product, essentially we need to relearn or create the science of soft material for many applications, much
mm.
beyond that science is missing. It's
Oh,
actually missing.
that's,
Yeah.
I think this is really excellent point.
Yeah.
And may I ask you, where do you think this problem comes from, that we don't have this kind of, yeah, this kind of concept of how we can commercialize that and making reproducible soft robot? Yes. Why do you think, what could be missing here
Missing
in
here.
what we
So
do?
there are a few immediate things missing, right?
Yeah.
One thing is for many soft robots, if you want to have, let's say, 10% strain or 50% strain, these are modest strain, but these are already quite large deformation. So the hysteresis, so loading and unloading may follow different curve. Right? That hysteresis itself is a problem for many applications. Or you need to deal with it or design material to avoid it. Also, uh, so if you want to have this kind of deformation, just survive for many, many cycles, fatigue is an issue. So car tires solve fatigue problem by reinforcements. So you have a lot of wires, metal wires, plastic wires, all kinds of wires inside the materials. It's a composite. It's not just soft material. Now, if you want to make robots, uh, will people be happy with composite? If so, what kind of composite? If not, do you need to develop new soft material to overcome soft fatigue issue? So you can do a very simple experiment with PDMS. You can try it at home, right? With a
Mm,
PDMS, you just make a little cut and do this as a cycle, 100 cycles, or just a rubber band, cut a cut, make a cut, and the cycle, the
mm,
crack will grow. So
mm-hmm.
we cannot tolerate soft robot has this kind of quality, right?
Yeah.
So he is a clear problem. Hysteresis is another clear problem. Also, are likely people will develop a composite because maybe homogeneous material is not good enough to fulfill all
Yeah.
the functions. Stretchable composite is another new field because for aerospace material, right? we develop, aerospace body now is a carbon fiber with epoxy matrix. Carbon is a terribly brittle material. Epoxy is a terribly fatigue-prone material, but somehow this composite is really tough, fatigue-resistant material, good enough for making airplane, right? So bad materials, when made into composite, can be extraordinary. That's known.
Yeah.
But that's airplane material. We should do the same thing for stretch material, soft material, composite, using, just ordinary material, make it fatigue resistant, low hysteresis, or whatever function is identified. So soft robots, and just in general, there's a bio-inspiration and a bio-integration. We're talking about, tissue engineering, really pose a whole new class of materials and the mechanics problem for the new generation. Some people are, just try to develop a new product, a new tire, new type of thing, like tire, have a massive appeal. But some people just focus on specific material issues. So it really is a broad enough range can allow many people working on this problem over many years. This is a very exciting time in the field.
Yeah. I think you really put excellent point. The first one about the fatigue issue, then we can't tolerate soft material. If you have a cut and make 100 cycle and just fail it. I'm curious to ask you then, yeah, we don't have so much really research on that. It just, we show the result, but we neglect some time at this fatigue or how it will be. And that's maybe the issue here we have to. I'm curious when you highlight the example of using epoxy and carbon, both bad material, and when you have it with them, it's just very tough. How you figure out this for soft material? Because, for example, we have a lot of trade-offs. For example, in ionic conductive polymer, sometimes if you have, for example, higher thickness and structure, you get higher forces sometimes, but the response is very slow, maybe because of the electrostatic interaction. I'm not sure, but this is kind of trade-off the material. And when you have to consider two bad material and give you interesting feature like toughness, and how you figure out that? How you figure out this material can really make a good chemistry in having toughness, high toughness? How you figure out this?
Yeah, it's an excellent question. So recently, in last 2-3 years, we and a number of other groups really zero in on this point. How do you create soft materials, which are also fatigue resistant soft materials? So we already said, so convince yourself soft materials are fatigue prone is very easy. Just take a rubber band, make a little cut. So rubber band, before you make cut, you can stretch this many, many times. So I used to have this experiment in class. I pass around a rubber band. So let's say we'll have 20, 30 students in class. So each student stretch maybe 10 to 50 times and pass to another student. By the end, this rubber band come back to me, is still working very fine. And then I just cut this rubber band with a short crack and pass around. After 1 or 2 students, the band will rupture. You can do this experiment yourself, with or without a crack. Rubber band, you need to have a broad width rubber band. You will see that the difference is just enormous. All right.
Yeah.
So if you make a large structure, you cannot avoid a small cut. If you avoid, it's not really a structure. Just think about the car tires, and you need to design material without small cuts for car tire. Come on, you're dreaming, right? Car tires need to be on the road. Robots need to deal with the world. You need to be robust, right? So fatigue is a clear issue from very early on. But fatigue in mechanics and materials has been 100-year-old problem, even older than Griffith. It was a known problem with very little clear solution, very little. But people also know something like a composite actually is quite fatigue resistant.
Yeah.
So I don't know how many people, certainly not in the textbook, clearly articulate why composite is actually fatigue resistant. So
Mm.
fatigue people, community usually worry about materials that has fatigue problem, such as metal, such as rubber, such as plastic. You have fatigue problem, I study fatigue problem of that material. So people haven't really spent a lot of time
Mm.
to ask a very simple question. How do I invent a new material that is highly fatigue resistant, right? So now for soft material, we have the opportunity, the question already posed very clearly because we need
Mm.
it and it doesn't exist. So then in recent years, we have borrowed this composite idea. All we need to do is we publish a number of papers already. Uh, do a composite. So you have a fiber, which is a stretchable fiber.
Mm.
So one kind of rubber. Matrix is another stretchable material. So both are elastomer, both are fatigue prone, bad
Mm.
fatigue. However, these two materials have a different modulus. So let's say modulus, Young's modulus fiber is 10 times that of matrix. When you do that, we made a demonstration. Yeah, this material is fatigue resistant. The fatigue threshold, for example, the number, we have number. So the way we measure how tough a material, how fatigue resistant, the number measure, but one clear measurement is resistance to the growth of a crack. If you do a monotonic loading, observe crack growth, this critical loading is called toughness. For natural rubber, it's 10 to 4 joule per meter square, energy per unit area, 10 to 4 toughness. But if you
Mm.
do cyclic loading, 50 joule per meter square. Orders magnitude poor,
Yeah.
right? So this 50 value was reported in 1960s, almost as old as my age, 1960s, and had not been changed in all these decades. But just in recent few years, number of us have demonstrated you can reach 1,000 joule per meter
Wow.
square as a fatigue threshold by composite, essentially. Yeah,
That's
just
wonderful.
ordinary rubber, ordinary hydrogel, you achieve
Mm.
fatigue threshold 1,000
Mhm.
by
And
orders.
how do you yeah, and how do you see the shape, or because we speak about shape changing, how the material can shape changes its shape. How
Yeah.
do you see the relationship between crack growth and the shape of these two material? Do you think it's play significant role, or just you have to place in, like as you mentioned, like matrix or lattice, for example? Do you think the changing of the shape has a strong relation or not with the crack growth? The shape of
It
the
does. It does. Shape has an effect. So we have demonstrated a few different shapes because we can use a 3D printing to control the shape. So we just say a fiber matrix, just straight fiber matrix,
yeah.
will give you that property, fatigue resistant. But if you have a crack going in the direction along the fiber, then fiber doesn't really stop fracture. In that case, you can use a 3D printing to make a lattice.
Mm-hmm.
So three-dimensional lattice, then fill the open space with a soft matrix. We demonstrate that. That will also work. That will work for all directions. The crack
Mm-hmm.
in any direction cannot go through. So, and also we submit a new paper. Uh, just say if you look at many biological tissue, one particular tissue, heart valve need to be fatigue resistant because it keep moving. That's a function of a heart valve. It's a
Yeah.
soft material, keep moving, so a billion times during a lifetime or something like that. You can 1 second a time, and how
Yeah.
many years you can calculate, right? That material is fantastic. So that material actually itself is a composite. People
Wow.
know about that. It's a composite. And recently we mimic this. We use 3D printing and use a medical image to just image the heart valve shape and then print it, a composite, and test it. Yeah, if you are not composite, you're terrible. After
Yeah.
100 cycles, several hundred cycles, you just have a crack growth. The shape is so weird. It's very difficult to maintain perfect structure. But with composite structure, it just lasts forever. We cannot fracture it. Yeah,
Yeah, I think this is very a hot topic and very interesting, very important. I think,
yeah, yeah,
yeah.
yeah.
So yeah, so we're close then, and the few questions are: do you think ego is important for the researcher? The ego is important.
What do you mean ego? You mean self-worth?
Yeah,
What depend on how you think ego. Ego, if in the positive spin, I would say uh, it's important. It's being in the sense believe in yourself and believe the problems that you care about will
yeah,
be helpful to other people. I think that's almost crucial, especially for somebody working on mechanics with such a long tradition of Newton, right? Who started new science or started science period, Galileo, right?
yeah,
Were direct descendant of Galileo and Newton. If you don't have some ego in whatever you do,
yeah,
you probably will stop doing it
yeah,
immediately. But if you have any sense of history and you will know what you do or what Newton did is minute compared to what human needs. Because Newton did
that's
not do solve robots, right? He didn't. He couldn't. Even he wanted, he couldn't. So, so there'll be always new things for you to do. Just believe in yourself. So there is a one American. I don't know if you know this guy. He's a local guy. Many hundred years, 200 years ago. It's Emerson. Has a
yeah,
Ralph Emerson. Emerson. You go online. Emerson, who used to write many essays. One of the essays, a very famous essay, titled "Self-Reliance." Self-reliance. Basically, he said you need to have some ego, believe in yourself. But on the other hand, if ego also has a bad aspect, right? It's
yeah,
right. It's just believing too much of your own worth. That is a I think it's a very damaging to people's health and relationship. The sooner you can get rid of it, the better.
I really like this answer. I think very, very excellent answer. Yeah. And I'm curious to ask you what may be the most important quality you have gained while being in academia. What is maybe the most important quality you have to maintain as a researcher in academia?
Yeah. So I guess it depends on the stages of a career.
Mm,
So for a student graduate student who thinks plan a career in academic, uh, so especially in United States, I'm most familiar because the different regions, Europe is somewhat different, China is somewhat different. In United States, the emphasis has always been on innovation. Yeah, you ultimately get respect as a researcher. You can become an administrator, which is also worthwhile endpoint for people. But if your endpoint is you want to just be a researcher, then the
yeah,
innovation almost is a single measurement.
yeah,
Everything else is about you get money to be innovative, and
mm,
yeah, you make friends to be innovative.
yeah.
Yeah,
But I'm curious to ask you a quick question here because I think in the podcast we speak about publish or perish culture. I don't know if in 80s you had this culture. Of course, they are brilliant researchers, but sometimes since the pressure to publish, papers, and sometimes if you want to explore and take your time and like fatigue example, just to try to make sure this material is fatigue resistant, takes time and experiment. How do you see the culture nowadays for publisher culture, since some people say it sometimes affect our curiosity and this, and people say we can do balance between both of them. How do you see this new culture? It was existing 80s before and 70s, or just something completely new nowadays? Publish culture.
It's an interesting question. So there is a really an excellent book published a few years back. The title is Reinventing Discovery, something like that, by this guy who also wrote a book, the definitive book on quantum computing. Michael, what was his name? Do you know who I'm talking about? He's a physicist and became a computer scientist. Anyway, the title of that book is Reinventing Discovery. It was an extraordinary book. The guy was just an exceptional writer. Anyway, he gave a nice perspective. The publishing actually itself has very short history. Very short history. It's essentially starting from the time of Galileo. So even Galileo, by his time, you can already publish papers, maybe not journals, you can publish books. Then when Galileo made his most important discovery, the discovery, I think it's about the satellites of Saturn, one of such discovery, he did not publish it. What he did is he wrote a secret message, scrambling words in those days, and sent that message, unreadable message, to a handful of leading contemporaries. I made a discovery. This discovery is in this code. That apparently accepted practice, so that he can secure his priority. Yet, nobody can read his discovery to build upon his discovery. That was a process. At a Galileo time. Yeah, Hooke, for example, our Hooke's law was also initially published that way, published as a secret code. The force is proportional to displacement. Was published by Hooke in this secret code. So I would say for people who want to have spent a lot of time on a problem, they have ancestor. They have distinguished ancestor in the name of a Hooke and Galileo. But I would also say time has changed. Research ultimately is a collaboration. I actually encourage, I feel people should really publish as much as they can and as fast as they can, so that other people can build on your result. So I believe the shifting culture of a value shorter papers, Nature, Science, PRL, this kind of PNAS, I believe it's created for a reason. I believe it's good. Just so that you have a rapid communication between researchers. And it's also because we can, right? Right now, submitting paper just one click away. You submit that paper, right? So whether the paper is only 1 page long, 2 page long, 3 page long, you don't have a postage issue, right? And a review is another click away. So you rapidly engage people in any new discovery. I think this will be the trend. The trend has already passed us. To criticize publish and perish, they simply did not know the history of publication. They just didn't know. They should read what's happened. what has happened. They should
Yeah.
not bring us back to the time of Galileo and Hooke. That's wrong. To keep research private to yourself, that's being selfish. And that selfish behavior rightly should be punished,
You're right.
should be punished by
Yeah.
other people publish ahead of you, should be
Yeah.
punished because you are being selfish, just like Galileo, just like Galileo. Yeah.
That's very wise words. I deeply thank you for that.
Yeah.
And lastly, what was the best advice was given to you and was life changing? Maybe personally or professionally, and was life changing for you?
Ooh,
You.
I'm
Yeah.
receiving so many good advice. Yeah, I don't know best. So, all through my career, I mentioned a few people, right? Professor G, my first mentor, then Hutchinson. When I went to UCSB, Santa Barbara, or as a young assistant professor, I had multiple mentors. Santa Barbara in those years was such a, still is a collaborative institution. So Tony Evans, David Clark, and Bob McMeekin, and Fred Land, Frank Zog. Just a name just goes on, and Fred Lecky. They all give me great advice. One thing it's interesting, and speaking of academic culture, things do change. So when I was assistant professor, I was encouraged to collaborate with everybody. So
Mm.
I almost wrote paper with every colleague, and nobody questioned my intellectual independence. Clearly, I was not independent because I wrote papers with almost all my papers were written in collaboration with someone. So, but nobody questioned me. They actually gave me tenure within 3 years. Oh, Zhigang, you're tenured. Move
Mm.
on. I was promoted to professor in 6 years. Oh, 6 years, you're a professor now. Move on. So nobody questioned my, yeah. But through these collaborations, I really learned the best of the people. So how they think, yeah, how they relate, things you can do in the lab, and an equation you write on paper to something real. Real, not just say this phenomena appear in nature, but also engineers can use this phenomena to do something better for other people. So that seemed to be the relation between reality and something you create in your mind and your lab seemed to be the ultimate thing
Yeah.
to do. That I learned from multiple researchers. Some of them are theoreticians, sometimes are experimentalists, some are more profound, always lost in thought. Some of them are more practical, always connected with immediate application. But they all have this translation between uh, between what's in people's mind and something real. That translation, just beautiful.
Wow. That's very beautiful. Do you have any final words maybe you would like to say as a community? Any final words you would like to say? Any final words you want to say?
So I don't know final word. So I just I guess just this Ralph Emerson's message was in 18 sometime. He was a local and lived nearby in Massachusetts. Self-reliance. So just a wonderful world has so many opportunities. You are never too late. So Newton did not solve all the problems, or whoever big shots in your field. The problems that engage you, make sure it engage other people. It will
Oh,
be if you do a good job.
yeah, so thanks so much, Professor. So I think this is really, yeah, thoughtful and beautiful. And I think you are a wonderful mentor and professor. And thanks for all the research you're doing. It's such an honor to have you on the podcast. I really enjoyed it so much. So thanks a lot for your time. Thank you.
Thank you. Thank you. Good
Thank
luck for
you.
you.
Thank you. Thank you.